Hello and welcome to today's video. In this video, we're going to introduce a new operation on matrices, and that is the multiplication of two matrices. Now, as a word of warning beforehand, matrix multiplication is not a lot like the multiplication that you know from the real numbers. It is quite different. We'll see in a few minutes how it is different and what to watch out for when multiplying two matrices. Still, even if it is different, matrix multiplication will turn out to be a very powerful tool that we'll make use of very frequently in the future. So, let's start this new chapter, and it's called Matrix Multiplication. Again, the idea is we will introduce a new operation on matrices. We already have the addition and we have the multiplication with a scalar, and now we're going to introduce the multiplication of two matrices of the correct sizes. Again, the concept may seem a little strange at first, but it will turn out to be a really powerful idea. I'll give you the definition right away, and we'll see a few examples of how this works a minute after that. We'll start with a simpler case. We will not multiply two matrices right away, but we'll start with a matrix and just a vector. Now, of course, a vector is a special case of a matrix, so that's our first step towards the goal of defining a multiplication for two matrices. So this is going to be matrix vector multiplication. To define that, of course, we need a matrix. So let A be a matrix with entries aij. We'll assume the matrix has m rows and n columns. And let x be a vector, and let's say x is a vector in R to the n. You will notice one thing, and this is n here and n here. That's the same. So this first n denotes the number of columns of A, and that second n denotes the number of rows of our vector x. And indeed, that will be a general theme. So these two numbers have to agree so that our matrix vector multiplication is properly defined. The number of columns of the matrix A must be the same as the number of rows of our vector x. Now let us define the product of that two. So the matrix vector product of A and x is defined as, we just write this in the form A times x as we usually write multiplication, and we define this in the following way. We take one row of the matrix A And we then multiply that row component-wise with the components of the vector x. We do this for every row. We add up the single components for every row, and the resulting vector is the result of our matrix vector multiplication. Now it sounds complicated. Let me write it down, and as I said, we'll see an example in just a few minutes. So we have the first row that starts with A11. We multiply this entry by x1, the corresponding x entry. Then we add the next component here. So we take A12, we multiply that with the corresponding x entry, which is x2. We add the next one, and so on, until we get to the last component. So that is A1n, and we multiply that by xn. And this is the first row of our result. And by now you should see why it's important that the number of columns of A and the number of rows of X agree. That's because we need to multiply the columns of A, or the components of that row vector, which are the columns, with the components of the X vector. So of course we need to have an agreement in the number of those components. We do the same thing for the other rows. So for the second row we have A21, we multiply that by x1. We add A22 times x2, and so on, up to A2n times xn. And this goes on for all the rows until we end up with the last one. So that's am1 times x1 plus am2 times x2, and so on, to amn times xn. So what we get is a vector with m rows. The number of rows is the same as the number of rows in A, and one column. There's a sum in each row, so each row is just a real number in the end. So this result is a vector in R to the m. And again, you notice that this m here is the same as the number of rows of A. Now, with this strange definition, what do we gain? Now, the first thing that we gain is we now have a convenient shorthand for writing systems of linear equations. Right? As you can see, basically, if A is a coefficient matrix for a system of linear equations, then what we have here is the first equation corresponding to that coefficient matrix with variables x. This here is the second equation, and so on, up to the last one. Of course, this is on the left-hand sides of those equations, but on the other hand, it shouldn't be too hard to add a vector for the right-hand side. That's just what we'll do. So this is the first remark, what we gain from this. Thus, A times x is a very convenient shorthand for a system of linear equations with left hand side A and variables vector x, vector x1 to xn. In fact, we can write a system of linear equations with arbitrary right-hand side completely in matrix vector form now. So a system of linear equations of the form AB can now be written as AX equals B. And of course, you'll ask, what advantage does that give us? It's even a little longer to write than the tableau form. It doesn't look a lot nicer. Well, the one advantage that we have is in this form, we have an actual algebraic object that we can do computations with. We could not do that with a tableau before, and we can do so with this matrix vector form now. So from now on, we'll only use this form to represent systems of linear equations. So this is the simple form of matrix multiplication, the matrix vector multiplication. And now we'll extend that to the matrix case. Again, that's a definition. And this time, this is the full matrix multiplication, not just a special case. But it is motivated by that special case. And I'll explain in a minute what I mean by that. So let's start with the necessary matrices first. Let A be a matrix. I'll call the entries AIK. And let's say this matrix is in R to the M by Q. And then we'll also take a matrix B. Entries BK, J. And this is a matrix in R to the Q by N. And again, you'll notice that there is a Q here and also here. So again, the number of columns of A is going to be the first matrix as before, and the number of rows of B will have to agree. And now what we do is we set this multiplication up in the following way. We take A as a left matrix, and for B we just say, well, B is composed of columns, of n columns, and each of those has Q components. So what we can do is we can use our definition of matrix vector multiplication for each of those columns. So we take A, we multiply with one of the columns of B, that gives us another column, and then we just put these columns side by side to obtain the final result. And that's exactly what this matrix vector product does, extended to the matrix case. Okay, so that yields the following definition. Then again, the matrix product of A and B is defined as, and this is going to look a little strange at first, but bear with me for a minute. We'll define this as A times B equals a matrix that consists of entries Cij, and I'll tell you in a minute how to compute these entries. And the size of that matrix, well, if we do it in the way that I proposed, we take this matrix A, we multiply with the columns of B bit by bit, and then produce the columns of the entresol. Then of course that entresol will have as many columns of B. So first thing you notice is the number of columns of B should also be the number of columns of the entresol. So we'll see an N here. What about the number of rows? Well, if I multiply the matrix A by a corresponding vector, then the result is a vector that has the same number of rows as the matrix A. So the rows of our resulting matrix, that should have the same number of rows as matrix A. So this here, this M, that will be the number of rows of our result. And let's see how to compute theseCij's here. Now what we do is basically for an entry Cij, we need to take the jth column of B, because the result is going to be in the jth column of the final matrix. And it's going to be in the ith row, so that is produced by taking the ith row of A. And we need to, again, multiply these two together by multiplying them component-wise and then adding up the results. So what we do is we sum up the component-wise multiplication of entries of A and B. The entries of A all come from the ith row, so there's an I index here first. The entries of B all come from the jth column, so the second index here is going to be a J. And then we just sum up the component-wise products. So we go through the row, that means the second index of this A is going to be a K, and we go through the column, that means we go through the rows of that BJ column here. First index of B is going to be that K. And this is also to be our summation variable, so we sum up over K from 1 to Q. And of course, we'll have to do this for all I and all J. So this is for I in M, J in N. So basically, what happens here is Cij is the product, so to speak, of the ith row of A and the jth column of B. So this is basically a matrix vector multiplication for each column of B separately. And please note, very important, the middle dimension of the two matrices has to agree. So A has to have the same number of columns as B has a number of rows. So this matrix product is not universally defined, but only if those dimensions actually agree. Okay, now let's first see a few examples before we go a little deeper here. First example, let's simply take two 2x2 matrices and multiply those. We make this 1, 2, 0, 1 times, let's say, 2, 1, 1, 3. What is the result going to be? Well, we'll start with the first row here of our left-hand side matrix. Now this will be responsible for all entries in the first row of the result. So we'll need that first row 1, 2, We need that for the first column of the result, and we'll also need it for the second column of the result. Again, for the right-hand side matrix, we'll also start with the first column. We need the columns of that matrix. Now the first column here will be responsible for the first column of our result. So let's start with the entry in position 1, 1. This one here. We already have the first row that will be needed for that. And we also need the first column. And then we just multiply those component-wise. So I'll write those below each other. So below the 1 here, below this 1 here, I'll write this 2. Below this 2, I'll write this 1. So that's 2, 1. And those will be multiplied. And then we'll sum up the results. Let's have a look at column 2. So column 2, row 1, this is column 2. We already have row 1 here, so the result of multiplying row 1 with column 2 is going to be in this position 1, 2. So we want to multiply the 1 with this 1 here, and we want to multiply the 2 with this 3 here. So there's a product here, and again, we sum up the result. So these are 2 entries of the resulting matrix. Now let's have a look at the second row of the left-hand side matrix, and that will use that for the same thing, basically. That will give us the entries in the second row of our result, here and here. For the first column, we again use this column here, 2, 1. And again, we multiply component-wise and we sum up the results. And finally, for the entry here, we use the second column, 1, 3. And we multiply component-wise and sum up the results. So we get a 2 by 2 matrix again, and the results are, well, here we have 2 plus 2, that's a 4. Here we get 0 plus 1, that's a 1. Here we have a 1 plus 6, that is a 7. And finally here we get 0 plus 3, that is a 3. So the result is this 2 by 2 matrix here, 4, 7, 1, 3. Now, let's try one more thing. You will notice that the left matrix and the right matrix, they seem to play different roles, right? The left matrix, we're using the rows of that. For the right matrix, we're using the columns. So one question that we should ask is, can we just interchange that? You know, we can do this for real numbers. In technical terms, multiplication in the real numbers is commutative. Is that also the case for matrix multiplication? Well, obviously that's not really true, because for matrices that are not square matrices, usually the reverse product would not even be defined because the dimensions don't agree as they have to. For square matrices, that's not a problem. We could interchange those two and the matrix product would still be defined. Well, let's see if the result is correct, or if the result is the same. So let's try 2, 1, 1, 3, 1, 2, 0, 1. Just change the order of those two matrices. Now what's the result of this one? Again, we'll start with the first row. Here's the first row of the left matrix, 2, 1. And let me do this one more time in that way. So we have this 2, 1, 2, 1. And here we have the first column, that is 1, 0. To put that here. And the second column, 2, 1, we need to put that here. And then we multiply the entries with each other and then sum up the results like this. And we can also do this for the second row here. This one, 1, 3. And again, we have the first column, 1, 0, and the second column, 2, 1. We need to multiply the entries and sum up the results. So that's our resulting matrix. And what do we get? Well, this is 2 plus 0. That's a 2. Here we have 4 plus 1. That's 5. Here we get 1 plus 0. That's 1. And here we have 2 plus 3. That's again a 5. And I'll compare the two results. Here's the results that we have. First one, second one. Obviously, the results are very different. So what we learned from this example here is that matrix multiplication is usually not commutative. The order of the two matrices matters. The result will generally be different if you change the order. So, matrix multiplication is generally not commutative. The order of the matrices may change the result. Okay, let's see. A few more examples. I'll try to be a little quicker for those now. So let's take non-square matrices for our next example. Like we multiply this matrix here. 0, 1, 2, minus 1, 1, 0, 0, 1 with 3, minus 1, minus 1, minus 3, and minus 1, 1, 0, 1. So what is the result of this multiplication? We have 2 rows here and 2 columns here. So the resulting matrix is going to be a 2 by 2 matrix. Let's start with the first row, this one here. And we multiply this with the first column here. And what we get is 0 times 3, that is 0, plus 1 times minus 1, that's a minus 1, plus 2 times minus 1, that's a minus 2, and minus 1 times minus 3, that's a plus 3. Then let's do the second row here and the first column here. That yields 3 plus 0 plus 0 minus 3. Let's go for the second column. We'll start with first row, second column. And we get 0 plus 1 plus 0 minus 1. And for the second row, second column, we get minus 1 plus 0 plus 0 plus 1. So altogether, the result here is 0, 0, 0, 0. So what can we learn from this example here? Well, the product of two non-zero matrices may very well be an all-zero matrix. And again, that's something that's not the case in real numbers. If you multiply two real numbers, but both are not 0, then the result will also not be 0. That's not the case for matrix multiplication. So the product of two non-zero matrices could very well be an all-zero matrix. And it gets even worse, and that's the last example that I have for now. If we take a matrix like this one, 0, 1, 0, 0, a square matrix that is not 0, and multiply it with itself. And that is abbreviated, as with real numbers, by just saying we square this matrix. And of course, this can only be done with square matrices. So what that means is I just multiply this matrix by itself, like this. Well, then, what is the result of this one? Let's take the first row again. First column, that's 0 plus 0. First row, second column, again, 0 plus 0. And for the second row, first column, well, that's all zeros anyway. Second row, second column, that's again 0 plus 0. So also here, the result can be an all zeros matrix. Okay, so that completes this round of examples. Before we go on to talk about rules of matrix multiplication, let's have a quick look at a special case. That's going to be a remark here. What about taking the product of a row vector and a column vector? Of course, those can also be regarded as matrices. A row vector is a matrix with just one row. Column vector is a matrix with just one column. Now what this yields is we have a 1 by q times q by 1 matrix. So the result is going to be a 1 by 1 matrix, or just a scalar. So the result of multiplying a row vector, like let's call this R, R1 to RQ, and a column vector, we call this C, C1 to CQ. Again, we need to make sure that the middle dimension agrees, is a scalar. Formally, R can be seen as a matrix, an element in R1 by Q. C can be seen as an element in RQ by 1. And that means R times Q will be an element in R1 by 1, or just R. So what this result is here, if we multiply R by C, what we get is R1C1 plus R2, C2, and so on, up to RQ, CQ. Okay, so basically it's one element of our matrix multiplication we obtain this way. So that is a very special case, as I said. Let's have a closer look at some other things that happen with this matrix multiplication, because it's often useful to be able to interpret a matrix multiplication in different ways. Let's say we have a matrix A with entries aij, and that is in R to the m by n. Let Cj be the jth column, and let Ri be the ith row. And I'll use Ri transpose because I want Ri to be a column vector just as C, and I want the transposed vectors to be row vectors. Okay, then for a vector x, we'll just take a vector x in R to the n and we multiply A by x. How can we interpret the result here? So that x be the vector x1, 2xn, be a vector in R to the n. Then A times x, well, what happens here? Is equal to, basically what we do is we can interpret A as a collection of columns. So we could write this as, well, this is the column C1, the column C2, and so on up to the nth column. This is the matrix A. And then we have our vector x1 to xn. Those are multiplied. And if we do this, we always take the first element of each row multiplied by x1, the second element of each row multiplied by x2, and so on, and we add up the result. Now the first element of row 1 or row 2 or row 3 is always the corresponding entry in the column vector C1. The second element of each row is the corresponding entry in the column vector C2, and so on. So what happens is that x1 is always multiplied with the corresponding element of C1. So this here is the same thing as, well, take the column C1, multiply that by x1. Then add the column C2 multiplied by x2, and so on up to Cn times xn. So basically what we get as a result here is A times x is a linear combination of the columns of A with coefficients x1 to xn. A times x is a linear combination of the columns of A with coefficients x1 to xn. And of course we can do the same thing for the rows. And in this case, we have to change our multiplication a little. If we multiply by a vector from the right, as we have just done, this will yield a combination of the columns of A, sorry. For the rows, what we do is we have to multiply with a row vector from the left. So what we do here is we have something like y1, 2, ym times, and now we have this matrix A that is composed of rows, row 1 to row m, like this. And the result of this multiplication, what that does is y1 is always multiplied by an entry in R1, y2 is always multiplied by an entry in row 2, and so on. So what we get here is effectively y1 times row 1 transpose, I forgot the transpose signs here, plus and so on up to ym row m transposed. So we have just one row as the result. Yeah. Well, the left-hand side matrix of this multiplication is this one. That's a 1 by m matrix. So the result will be a 1 by something matrix. And that something will be the number of columns of this one. So to sum that up in a more concise form, we could say the column space of A, that is all linear combinations of the columns of A, that can just be written as AX, and we just vary X. So we could say the column space of A is the set A times X, where X is in R to the N. We can do the same thing for the row space. The row space of A is basically Y transposed A with Y in R to the M. And to be precise, the row space is usually also considered a vector space consisting of columns. This here would produce a row. So to be precise, we would have to transpose the result again. Yeah, but just a technicality. Yeah, it's not really important here. And finally, the kernel, let's add that also for completeness. There's nothing like that for the kernel, but I just want to repeat what the kernel is because it fits nicely here. Again, that's all x's that have the property A times X equals 0, and that is the 0 vector here. So we can also write this linear equation system in that concise way now. So that concludes this introductory video on matrix multiplication. We'll see more matrix multiplication in the following videos. We'll have a video on the rules of matrix multiplication. And of course, we'll also see some applications of that before we go even deeper into that topic here. So I'll see you in the upcoming videos.